Okay, last day of notes. I am going to break this down into 3 different videos. We're going to look first at electrolysis. And in electrolysis, what you're doing is you're causing a non-spontaneous reaction. So we know what that means as far as voltages go. It's a negative voltage. And we're causing that non-spontaneous reaction to occur. And the way we do that is by giving it a push from an electric current that is provided by a voltaic cell. Some sort of battery usually provides that. Typically, when we have electrolysis, we're talking about an ionic compound that is going to be electrolyzed. And if you remember back to almost the beginning of the year when we talked about conductivity of ionic and covalent compounds, things like that, we said that ionic compounds conduct electricity, and they only do that if they are either aqueous, so in other words, dissolved in water, or if they are molten, so in other words, a liquid. So this would be an aqueous solution, and for molten, we're talking about liquids. And this is just really because otherwise the ions are in fixed location, so we need them to be able to move around freely. So that's the key to this, is that they have to be able to move to be able to conduct electricity. So that's why they have to be either dissolved in water or molten. And we have some general rules that we are going to follow, but these are pretty easy. It's not even something you have to feel like you have to memorize because it just comes naturally. If you're talking about you want to be able to predict what the products of the electricity will be, then you know if you have a pure molten substance, so again, we're talking about a liquid, right? So our Joe generic substance might be sodium chloride, which would be in the liquid form because we're talking about molten. Then we know that the cation is going to be reduced and the anion is going to be oxidized, which makes sense because when you look at this, and if you think about it, those ions being able to move, that means it's breaking down into sodium ions and into chloride ions. So as far as the reduction goes, it's going to be your cation, in other words, your sodium, because it would have to be that in order for us to be able to gain those electrons on the left-hand side. That's showing us reduction because of this positive value on the left-hand side. And then, of course, oxidation is going to be from the anion because in that case you've got your chloride ions going to chlorine, and then we have to balance that by putting the 2 there. This is going to be oxidation because you've got your 2 electrons on the right-hand side. You're losing those electrons. So what we see in these rules makes sense to us, that your cations, just by necessity of how it works out, are always going to be reduced, and your anions are always going to be oxidized. You just go back to what your original ions are, and it will always work out that way. So if water is present, in other words, let me just head back here real quick. Everything that we looked at on this page, or not this page, but this little paragraph, is talking about a liquid. So now what we're looking at is an aqueous substance. So now we've got water present. It's not molten or in solution. And we've got something else playing a role in this now. We have to be able to decide whether water will react or if the ion from the salt is going to react. So now in this example, we would have not only do we have sodium chloride that's aqueous, so breaking into those 2 ions, we've also got H2O to worry about. So that's the difference. And we're going to just really use what's in bold here as far as a way to remember this. There is some information in the book that is a little bit more complicated. We're just going to go with this simple idea that group 1A or 2A, in other words, your alkaline metals or your alkaline earth metals, they will be reduced in an aqueous solution. I'm sorry, let me rephrase that. that they will not be reduced in an aqueous solution, but instead your water will be. So your alkali metals and your alkaline earth metals will not be reduced. Instead, the water will be reduced. And then the other part of this is that your polyatomic ions, that's your anion, and instead of that being oxidized, the water is going to be oxidized instead. So I know this doesn't make much sense until we actually see it used in an example. But let's do a couple other things first. First, here we just have some basic differences that exist between a voltaic and electrolytic cell, so it's good for us to know these. First of all, we've already learned this, that we know a voltaic cell is spontaneous, whereas an electrolytic cell, you have to give it a push because it's non-spontaneous, so you have to force it to occur. A voltaic cell, the way we've been diagramming those is we've always drawn them as two half cells, and then we connected it with the salt bridge. Whereas in an electrolytic cell, what we see is it's just going to occur in one single container. So we'll draw those here in just a minute. And then in a voltaic cell, this really goes back to that first comment that I just made. Voltaic cell is a battery, and it produces electricity. Whereas that electrolytic cell, remember, it needs that push, it needs that battery in order to occur. And then finally, this is kind of the toughest one, the biggest difference here for us to think about is that electrons flow from the negative electrode to the positive in a voltaic cell, while the opposite is true. In an electrolytic cell, the electrons flow from the positive to the negative electrode. So let's add a little bit more to this. Let's mention that regardless of cell type, we're just going to say fat cat. Hopefully you know what that means. Regardless of the cell type, the electrons are going to flow from the anode to the cathode. Doesn't matter if you're talking about electrolytic or voltaic, that's going to be the case. So what that means, the difference that we're going to have is the charge of the anode. And what we see, there's a couple different ways you can remember this. You can remember that Vanna works for the EPA, or an EPA van, something like that. But what this tells us is that in a voltaic cell, the anode is negative. So let's just say anode negative. And in an electrolytic cell, you have a positive anode. So here we have an anode that is positive. So that's the biggest difference. That's what that blurb is really trying to tell us, is that we have different charges to our anodes for the voltaic and electrolytic cells. It's still always going to flow from the anode to the cathode for your electrons, but you've got different charges there because we're giving it a push. So now let's go ahead and do one example where we've got a molten case, and we've really done a lot of this already with our examples, but if it's molten and it's sodium chloride, then we know that we're really just talking about NaCl, which is liquid. So in other words, those electrons are going to be, those ions are free to move, so we've got sodium ions and we've got chloride ions that we're going to have to deal with. The way we draw this is we draw one big container, and in that one big container I'm still going to have some electrodes, but I'm going to make those electrodes out of some sort of inert metal, and the most common one used is platinum, PT. So I've got a couple electrodes made out of platinum. These are going to be connected to a battery. Not a voltmeter like a voltaic cell was, but a battery. And there's a couple different ways we can draw this as well. Maybe you want to just do it like this. Sometimes you'll see them drawn. I'll just try and find a little spot over here and then I'm going to erase it. But sometimes you'll see it hooked up like this, and that's just a schematic showing what a battery looks like. So you see those parallel lines for a battery sometimes. So there we go. All right, so with our battery, we're going to have, we could say that we've got, let's just arbitrarily call this positive and this negative. So just to bring it down here a little bit closer to C, we've got positive and negative electrodes. And all of this is in a solution. And in this solution, remember, think about what this solution contains. It's molten sodium chloride, meaning we've got some sodium ions and we've got some chloride ions in our solution. So since we have said that this is the positive terminal over here, we know that this is going to be, remember, it's an electrolytic cell, and you remember that Vanna works for the EPA, so the positive is going to be your anode, whereas the negative is going to be your cathode. So that's a big difference. Let's go ahead and do some calculations. We know, in fact, if you want, you could even just write it underneath each side, each electrode. I know that my reduction half is going to be my metal. My cation is going to be reduced. So your sodium ions go to sodium, and then you add an electron. And then for your anode, you've got your chloride ions going to chlorine gas. Well, we have to put another 2 there because to balance our chlorines, and then add a couple electrons. So as long as we're thinking about this, we can go ahead and really get it balanced. And I look at my electrons, they don't match up, so I need to add another, I need to multiply this through by 2. That's what I'm doing here. And so we get 2 electrons plus 2 sodium ions goes to 2 Na. So we have our 2 half reactions. I could tally this whole thing up and get 2Cl minus 1 plus 2 Na plus 1 goes to Cl2 plus 2 Na. Okay, so we can also label then our oxidation and reduction halves. We've said it out loud, but we haven't written anything down. So we see that our chlorine is being oxidized. So I can go ahead and label this over here. And I see that my sodium is being reduced. You know what? We knew that from the very beginning. We said that your cations are going to be reduced and your anions are going to be oxidized. So we knew that from the beginning. We really could have started with that if we wanted to. And then, really, I guess what this is asking, it doesn't, oh yes, it asks what are the products of electrolysis. So when we look at this, we can see that our products are going to be these 2 guys. We've got some chlorine, which is in the form of a gas, and we've got some sodium. So I'm just going to over here write products are chlorine and sodium. Now, since you've got sodium that is going to be a product here at your cathode, that's a solid. With your chlorine being a product here at your anode, what you would actually see if you were to perform this experiment is you would see some bubbling taking place. So yes, it is common practice to go ahead and show those bubbles in your diagram to just make sure that we know that this is a gas that's actually being created at your anode. And I think that should do it for our molten one. I'm going to do the aqueous one in another video.